Hey everyone, welcome to another episode of the Common Lisp Study Group. I'm your host, Ron Batum with Atlanta Functional Programming. Today we are going to be discussing part three of our overview of the honestly ever surprising and continuing to surprise me library, Colton. This is a static uh, this is a library that gives you, as I mentioned in previous episodes, static typing in a Haskell-like sense, and to the Common Lisp language, and it integrates actually quite well with Common Lisp, so you can now interact and build um, properly Haskell-based static typing into your language, into your like applications and your libraries, and it augments the current already available Common Lisp type system so that you can actually pick and choose where you want to use what and actually work through and provide a different development lifestyle than what you would normally be accustomed to if you're using just Common Lisp alone. And allow it makes us, it kind of gives a realization to folks who are coming into Common Lisp that hey, you can actually build other languages into this already beautiful language and allows you to do some pretty amazing things. Um, Today I am going to be covering in this particular episode in part three, the discussion on type classes and what is available in Colton for from the type class standpoint. This is a particularly interesting topic because, type classes is a very fundamental feature that is built in Haskell. It's actually what it uses to uh, provide some, what we would consider well-known abstractions and for doing higher order functional programming, particularly in the statically typed world. And for those who aren't familiar with Haskell, I'm talking about features like, say, monoids, semigroups, functors, applicatives, and monads. um, for the C++ people in the audience who haven't been updated in modern C++, I'm not talking about functors like callables as they used to be i- incorrectly called in pre C++ 11. Um, I'm talking about functors, which actually addresses a particular type of algebraic type, and we will address those, as we, um, visit those particular topics. But first, we need to kind of understand type classes, and we need to understand monoids and semigroups, and work our way up into the monadic world, and what is provided inside. Haskell. Sorry, inside Colton, which it kind of picks up quite a bit from Haskell. One thing that I think I should point out at this point is while we are covering a lot of stuff that's familiar with Haskell users, I'm going to assume that haven't touched Haskell in your life. So we're going to be going through kind of a type class 101 again today for folks who want a more rigorous version of that, and with examples in Haskell, I encourage you to go and look at AFP's Haskell study groups episodes where we actually cover the topic in more detail. So I'm going to rush through a couple of the things on what a type class is, just for brevity's sake, so that way we can get into some code. But at the same time, I have done a more thorough review with Haskell, and if folks who want to understand how to do it and leverage it the way Haskell does, and want to understand what they provide and kind of do a compare and contrast, I encourage you to go look at that video, and I'll put a link into the YouTube description for after we're done today, so that folks can have a good idea on what's going on there. Additionally, regarding this Haskell versus Common Lisp thing related to type classes that I think is important to know is the fact that there are a couple things that Colton has changed with respect to some of the built-in type classes, um, and well, it tried its best to kind of make sure that things are seamlessly integrated between the Common Lisp world and the Haskell world. And for that to work correctly, Colton actually made some particular design decisions so that code that's in Haskell that adopted a particular pattern, like say the functor pattern using fmap, you're not going to do a one-to-one port of that code into Colton and have it suddenly work as is. There is a couple of things that you need to change. But since we're not going to cover a lot of those higher level type classes now, we're going to do it in subsequent episodes when we cover functors, applicatives, and monads in Colton. I want to kind of postpone showing you those differences until we address them there. So this way you are at least aware of it at that time, and you can do a proper, registration between, what we're going to be using based on the examples we present there. Finally, in addition to getting some pre-built type classes and stuff that we did that's in the standard library coming from the Haskell world, Colton actually took a page out of Rust's book and provided two type classes that are part of traits that are in the Rust programming language. So hopefully today I'll have some time to at least briefly mention a couple of those. I won't go into too much detail with some of those just because first I'm not familiar with how Rust exactly leverages these type traits, but I will at least point them out accordingly so that if some Rust expert comes in and says, "Hey, you said something, incorrect here," or they can properly give me, or give us a kind of an overview of some of the nuances that weren't actually covered in Colton. At least that would give you some idea on how to adopt those particular type classes for your uses in your code. So, what is a type class? I think that's kind of the first thing that we need to kind of discuss. Uh, a type class in um, the purest sense, when you're coming from the Haskell space especially, is nothing more than kind of the way they defined it is kind of like an interface for types. Okay, so at least this is how I kind of explain my understanding of it. So the idea is um, when you are developing, sometimes you may have a series of concrete types that all representationally are different. So meaning that when you lay them out in memory and so forth, they all have different, memory layouts. They may have different members. They are literally disjoint types at a very fundamental level. But the way that they interact with algorithms, they may share some common characteristics. All right. An example of this actually would be, uh, say, if you are talking about integers. All right. Integers have many different types of representations, um, depending upon what size of integer are you talking about. Are you talking about a 8-bit integer, 16-bit, 32-bit, which is the fixed width of the word side that was on the machine, because we've gone from 8 to 16 to 32 to 64 now, which we have very large numbers. Are you talking about signed integers or unsigned integers? Are you talking about, uh, rationals? All right, like fixed points, where you are representing a floating point number as a fixed num. There are so many different types of variations in there that it becomes difficult to recognize each representation of it. But all of these are integers, okay? And they are actually different from, say, floating point numbers, which have their own machine representation. But when you are talking about addition or subtraction or any of the basic arithmetic operators, you're not actually going to be dealing with um, uh, the representation there. You're just talking about a number, right? a specific the underlying representation or the type of it is irrelevant to the actual operation. The operation should be able to determine that this is a supported type for this type of operation. This is a lot of what allows you to then do some sort of generic programming. So you can have one implementation where you have these methods, these operations that you know your set of types are going to support, and then um, those types, when they actually implement those operations, they make themselves available to using those algorithms. Okay, this is how generic algorithms and generic functions are kind of actually implemented in languages that support this particular feature. It's a form of, you could think of it as a form of, say, um, uh, genericity, and it can sit on top of any system that supports parametric types. Um, so to begin with, let's fire up our Sly and start our little project here. And uh, to kind of give you an idea on what I'm talking about, since I mentioned integers, I think it's probably best to first do a Sly apropos and see if I can get Colton num from this. Let's see. Go down here and let's look for Colton. So this is not in here. Let me see if I can actually restrict myself to Colton specifically. Colton. Let's see what this is. Describe Colton Library and num. It is a symbol. Where is it used? Sly. Yeah, let's see here. This is back to definition. I would say that nope, that's not going to work. Okay, so let me see if I can actually do, let's see, open, let me do this. Sly, describe symbol, Colton Library num, and we know that it's there. Not that. 4. I want to see who specialized this on this symbol. Sly. There we go. Okay, so this means that this is in the library, but this isn't actually properly integrated into the rest of the things. Okay, that's a bit disappointing. Okay. All right. Looks like I can't do what I was hoping that I would be able to do today. Well, not today. It's just that I was hoping that there was a better integration with the Colton library, so that we can use Sly's features to go introspect to see what implements the num type class. So for folks who aren't familiar with Haskell, Haskell has this feature where you can actually go and look up a particular type class and figure out what types define it. Okay. This is a notion of defining quote unquote an instance, which we'll touch base here to in a minute. But If it doesn't, that instance is what registers that type into leveraging that type class. And more importantly, it's that registration which holds those implementations that allows anybody who calls an operator on instances of those specific types to recognize that the appropriate type class, because what it does is it does a lookup essentially into whatever dictionary that represents all the implementations that's available, and it will then execute if such a thing exists. In Common Lisp, of course, if you are using clause, it's very similar to saying like doing a generic function lookup. But there are some small differences in terms of at what point in the compilation process that's happening. I think, if I recall correctly, Common Lisp Object System does all that stuff at runtime. It doesn't. It may attempt to do some of that stuff at compile time, but uh, usually it errs on the side of caution and provides a few more instructions to actually go and do the lookup, unless you've done some explicit type declarations behind the scenes. All right. And folks who are watching on the stream, as well as in um, our our meetup on the Jitsi, feel free to interrupt and ask questions. Folks who are joining us on our Jitsi link, just to let you know, there is a hand raising facility that we could actually leverage to actually, if you guys have questions. And those who are not or are part of our stream, if you are a member of the AFP meetup, the Jitsi link is available at your disposal on our announcements. But let's get started on at least talking about um, how to define a type class, okay? And then I'll give some very concrete examples on creating functions associated with it. Um, the first thing to note is when you are defining a type class, there's two things you want to first be aware of. One, you want to first make sure that the type class does not already exist in the standard library. The reason is if it's there, then what you really want to do is actually implement an instance of the type class, all right, that's already available, not create your own. That's best practice in languages like say Haskell, as well as best practices on any if you're implementing any specific implementation for a given type on any programming language in general. I would or framework, if you're just leveraging the framework, I would just go ahead and follow that practice here, even in the type class world. There's no reason for you to do this. That being said, to simplify things, I am going to go ahead and rewrite, say, the EQ type class, just so that folks can actually get a taste of what it is to define a type class and what it is to actually uh, implement a type class for a particular uh, uh, type. The one thing that I'm going to also point out right now is there is going to be a small difference coming from the Haskell space into the Common Lisp space. But again, Colton is still a very new library. It's still pre 1.0. It might be at some point in time that they are going to go and change this. And when that happens, obviously this would be even better. But beware, what I'm about to show you. It The current process is this. It may change. Hopefully with newer releases, if they figure out the challenges here. So what am I talking about? So when you first define and actually let me first set my package here. Go here, set package, and let's do AFP Colton overview. Okay, so we now switch to package here. So when you are defining a new type class, you need to use essentially something called define class to actually define this. Okay, so this is following the same um, conceptual design that Haskell provided for defining type classes. So when you're defining a type class in Haskell, you have the same, you have to use class and then the name of the type class to do it. It's the same design conceptually that they've adopted, that Colton adopted. This involves you first defining top class. Folks who are just looking at this wondering why I'm not, exposing or prefixing Colton top level and define class with a Colton colon. Just recall that in this project, our package actually already leverages and uses the Colton and Colton library because the Colton library symbols are many of them, there's many duplicated symbols between the Colton and Colton library packages and the standard Common Lisp package, which is why we're not actually um, using Common Lisp like you would normally do with a normal Common Lisp package. Once you've defined the class, you're going to have to also specify a name with it. Since EQ already exists because of Colton, we are going to name our equality class my EQ, and it will take in a type variable. Recall that type variables are represented in Colton using keyword arguments. Now we are going to specify the operations that we want to be available in order for the Colton type checker to recognize that a particular uh, instance has first off adhered to the type class definition interface that we're providing here. But more importantly, it allows a type checker to recognize that what an argument is being passed into, it satisfies this type class constraint for the operation to get executed in the first place. All right. Since equals equals and not equals, which is typically what's used for equality, um, exists already as part of the EQ type class, I'm just going to go ahead and take a page out of JavaScript's book and make triple equals as being a stronger equals. All right. Now, although this is going to later on reference equals equals behind the scenes, because I don't think it's necessary to have strong equals, equals equals, and strong equals should be both the same thing. But um, for now, we're just going to go ahead and define this because this operation doesn't exist. Okay. So when you're defining a new what's it? A new operation as part of a type class. The syntax form is basically when you are, so yeah, I'm not sure if this gets highlighted. Let's see if we can see this. Yeah, it gets highlighted. All right. The first part is our actual operator name. Here we're using an actual operator. You could certainly think of this being a function name if you really want to. I will create equivalents to those too as well if that would help. But you will see in a minute why I'm going to simplify this interface for our implementation needs. The next thing is a function signature. Since this is going to be a parametric type, because the parametric type is, I mean, the type class itself is dependent upon a parametric type. Uh, our function signature is going to assume that they're going to be getting any sort of the type variable that was passed into the type class instance. So when you're defining the type class, you're going to have to, an implementation for the type class, you're going to, when you pass in whatever in replace of this variable, this type variable, it's going to get injected into these type signatures. So everything gets properly type checked. Here, we're specifying that our equals 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 operator is essentially a curried function that takes in two arguments and returns a Boolean. All right. Um, we're also going to specify a not equals equals just so that we are, I can also talk about this other thing, this little caveat that I learned from regarding type classes. And this is our basic interface, okay? You don't need to specify any sort of default implementation. You could really think of this as a proper interface. All you need to do is specify the operations, and that's it, okay? And this really is our first type class, okay? That's what a type class is, All right, it's a series of operations associated with the signature. All right. Um, but that's not so overwhelming, right? But right now, this type class, even though it's been defined, it cannot be used because there are no implementations of this type class for any type. All right. We have to define it just like we have to define an implementation for an interface in order for an interface to be properly. There's no way of instantiating this. The type checker is going to use this information later on to recognize that things are of a particular type class so that it can do whatever it needs to do. But from the standpoint of development, you can say that this interface is just meta information that required for later on. So we need to go ahead and implement a version of this. And this brings us to the first difference of the first difference between type classes in Colton and type classes that are specified by Haskell. So first, when you're defining an instance of a type class in Colton, you have to use something called define instance, okay? And the notation is obviously it specify the type class name and you're specifying what you are defining it on. All right. The next thing to do is recognize something here that type classes don't provide in Colton as of yet. All right. And that is there's no notion of what is the minimal implementation of the type class in order for something to be recognized as being a type class instance. Okay. Normally, for example, in this case with equals and not equals, one would define either or and just simply have the type class generator generate the definition for the other function. Colton currently does not support that generation yet. I think I'm not gonna uh, speak for the project because I'm not a member of the core project there. But I could say that I don't know if they're currently working on it, but I hope they are. But in the meantime, because it doesn't generate based on a minimal implementation, what we have to do is we have to define every function for every function represented in the type class, which means we have to define a version of equals 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 and a version of not equals. Now, although you could certainly do one and just say not the other, and you'll be good to go. So in this case, when we define um, our instance, we're going to go ahead and we're going to define equals equals and just say not equals is a version of calling equals equals by calling not on equals equals. So here it's pretty simple. What you do is you define in the define instance all the functions that are representing of that type class. So it has to be scoped, okay, into this area. Otherwise, it will not recognize that it was been defined. And then we just go ahead and do our normal thing, right? We can just here in this case, I'm being very um, naive implementation wise. I'm just directly redirecting my equals to equals equals because they are kind of one to one in this case. And obviously, in this case here, I can do not equals equals AB and just say not AB. And I think if I remember correctly, Colton Library. Pretty sure not is available. Let's just make sure. Colton Library. Yeah, it's there. All right. So we have our first type class instance. And now if we actually go and try and use this, which you can do here in this particular case, we could just say equals equals 1, 2. You could see, oops, sorry. We do equals 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 1, Colton equals 1, 2. You see that we get a Lisp nil. If we do Colton not equals 1, 2, you'll see that we get true. And of course, if we try to specify anything that was not defined, that were not defined on here, like if we try to attempt to do 1.5 and 2.7 or something like this, we'll get a type check error because it can't actually reduce that. That's what they mean by fail to reduce context my equals SQL float and Colton. That's basically it attempted to essentially see if there's a it recognized that these functions have a type constraint, that this needs to be a MyEQ instance. It couldn't go and do a lookup and find a single float version of this, and therefore it's just going to go ahead and throw that up. Nothing spectacular here. Obviously, this one is pretty simple. Let's actually go and define a version of this with for our example for my color, which actually, as you recall, we have our color defined here as a type of red, green, and blue. It's an enumerated type. Okay. Now, in this case, obviously, you'd want to leverage um, the match expression syntax that we looked into, right? So let's go ahead and do that. Let's do a match on the tuple structure of the arguments. And in here, if you recall, to get the match, we have to provide all the different, a couple of cases, right? So in this case here, we're just going to go ahead and, it's kind of like cond. So you provide the pattern that you want it to look for. In this case, we'll do tuple red, red, and then we could just go ahead and specify the condition. Um, 1 second here, getting. Um, all right. All right. And we'll do this for the couple of other cases here. Blue, blue, true, and then tuple, green, green, and then this is going to be true as well. And for all other cases, in the match syntax, if you recall, we can actually use the underscore to specify that we don't want any other cases here. All right. And we go ahead and we can just go ahead and compile this. Complete instance of my predicate. Da 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 da. Red, green, blue, false. Hold on 1 second. There is something that I messed up here. Mm. Sorry. I just realized that I have to also define not equals, not. All right. Now we're good. So if we go ahead and now, call equals on red here, and obviously we're going to have to make sure that we call Colton in this because we're doing Colton expressions. We'll get, what we're expecting. Now, again, recall that the reason why we need to specify the Colton expression is behind the scenes, each of these operations gets what's called a dictionary object, which is essentially nothing more than an argument to the Colton environment. The Colton environment object that holds all the symbols registered with Colton is separated from the Common Lisp namespace to include some stuff. So Colton is a convenience way of actually injecting required that required dictionary into each of the operators that are specified in there. Are there questions about what type classes are? I'm just going to pause for a minute because it's important to understand this may look like just, interface and implementation differences, but what we have done here is we've taken a the idea and this is the beauty of just this pattern of defining the type class. We've taken what would be normally an interface for a single hierarchy when you're looking at object-oriented languages, all right? And we basically said, we're going to have this be an interface for a family of types, all right, that all share this common characteristic. There are many different types of uh, type classes available to you at your disposal from Haskell that Colton just adopted as is. EQ is one of them. As I mentioned, but in addition to that, there's also order. So ORD, all right, for ordinal, it'll make sure that types are orderable. So if you specify ORD, you need to recognize that they are that the less than, greater than, all the relational operators related to sorting must be available in order for things to be essentially an instance of ordering. Num, which is for numeric types. This includes what we were talking about earlier about different types of integers, um, fixed nums, floating points, both single and double precision, as well as uh, rationals. If I believe, actually, I think rationals may not be in there. Um, that's that's an interesting question. Actually, I've never. I just I don't remember if this will actually work. Um, um, second here. Okay. All right. So let's see something here. 1 plus uh this type of here. If I do 1 divided by 2, we'll see invalid arguments. Hold on 1 second. I did the wrong thing. Here, do not type something. Hold on 1 second. I think I did. What was it again? It was type of 1 divided by 2, but was, yeah, sorry. I keep forgetting that I have to do this and do Colton. Type of unknown bounding in Colton. Hold on. Oh, type of actually exists in Colton. Let's see if I could do library type. Type of Oh, 1 second. Did I just mess that up? Unintern of I am totally unintern. So if you don't do that, there's going to be stuff in the Colton namespace if you don't unintern the symbols. So it's always like kind of good um, hygiene to actually go make sure that you are cleaning up your symbols table as you're going through this. Let's make sure that we've done. Let's see here. What was I going to do? Oh, we've done this before. Right. That's what I have to do. This, if we do plus Colton plus the fraction 1 divided by 1 in 4 with the fraction of 6 actually works. Yes, this actually works. 2 by 12 plus 2 by 12. Yeah. So you can see here, what I was trying to do is if you look at type of, you can't actually generate fractions, right? Because we've talked about this. The divide operator requires a dividable instance, and there's no actual implementation of dividable for integers and anything. It doesn't just do simple raw division. Um, so we had to go and actually cast it using the operator as a fraction, which is defined in Colton. We're not actually using, if you remember, if we do CL type of is a different implementation, and then we do CL divide 1 by 2, we get a ratio. Very different definition, different implementation. But because they have their own environment object, they're able to coexist without having any troubles. You just gotta remember which space you're talking about when you're going into their different type systems. So obviously, when you're building larger scale systems, you want to isolate, these implementation kind of details, so that way your end users don't recognize what you're trying to do. And as long as you stay within the Lisp world, um, or within the Colton world and kind of document it as such, it will make a pleasant API experience for folks who are developing applications using your libraries, using and leveraging Colton especially. Um, but the main reason why I bring this up is plus, since fractions are considered a numeric type, plus obviously is going to be defined on them. All right. We're going to be discussing plus a little bit more in detail today. Like, I know most people know about addition in general, but plus is very special when it comes to numeric types, and has is multiplication. And it's going to be brought up when we start talking about our next topic, which is going to be on monoids and semigroups. Well, we'll try and touch monoids. I don't know if I will have time for semigroups, but um, uh, no reason to rush rush the concept and rush the idea. Um, the other available type classes, all right, is actually, since I brought them up, um, semigroups, monoids, functors, applicatives, monads. There's a thing called alternative, which I never really quite understood still. That's available in Haskell that Colton adopted, and has part of um, so if you this is from Haskell specifically. EQ, ORD, which is orderable. Num is for numeric types. We have semigroup support. We have monoid support. We have then our good old FAM, functors, applicatives, and monads. All right, and there are a bunch of monads already defined too as well. But obviously we're gonna have to deal with it. Um, the one thing that I want to bring up before we start digging into implementing some of the the other types there, which because I think honestly, really, this I will. What I'll do is I'll finish off the Colton library overview today, and then probably be better to like cover uh, the the for implementation of the types in a separate discussion on um, in our coming weeks. Just because, as many of you know who have been following along in our Haskell study group as well, we're covering the same type systems. But I'd like to think of it as a separate discussion topic, just so that that way we can actually separate from using Colton and actually thinking about these other higher level concepts. Um, so there's two more things that I'm just going to bring up. One is from Rust, the type traits into and try into, which gives you the ability to actually do conversions from one type and another. And then the other thing that I'm going to bring up is the fact that um, because we have monoids and monads and functors, uh, Colton actually adopted uh, the do macro, the do notation that's popular in Haskell to define sequences, and that's something that's important to recognize. In fact, I think we may have at some point used it, but I don't remember. No, we haven't. Okay, perfect. Okay, we'll go ahead and do that then. All right. So, let's show a new version. We're going to generate a new top level here. Actually, you know what? There's no reason to create a new top level. We'll go ahead and start our next thing, which is using do notation. What is do notation? When you start talking about in the Haskell world, all right, and in statically typed worlds that leverages type classes and in particular static typing, okay, and more importantly, static type languages that implement functional programming constructs, okay, for higher order functions. One thing that becomes very apparent is since things are immutable and stuff like that, there's may not be any guarantee that things are going to run in a particular sequence. Obviously, the exception to this is if you're using IO, the monads, and particularly the IO monad, in being one of the more popular ones that like illustrates this. So we need some way of actually saying, look, composition wise, we expect that when you're doing particular assignments, that things are going to happen in a particular sequence. So we can more or less guarantee that uh, we could do we we can leverage them when we actually apply a function to its arguments. All right. So when we're dealing with things like IO monads and monads in general that leverage this kind of sequence, one way of putting these things into sequence is to do the do notation. So let's take an example of a function. Let's say we have a function with two arguments. Okay, we'll call this f prime, and we'll say that it has two arguments, AX and BX. This is a reference to the example that's available in the intro to Colton README that I thought we would go and discuss. In this example, what we do is we define a function using the scheme notation that we see here. Then we're able to do here. Now, do again is being defined differently than do in Common Lisp. Okay, I cannot stress this enough for folks who are just joining us and looking at this as examples. Very important to realize and recognize that the do notation here, all it's doing is saying run the next set of forms that is scoped within this do block in sequence, one after the other. So we can certainly take, for example, um, A as being, you know, something unwrapped from AX, B is from being something that's being unwrapped from BX, all right? And then we can then define a C as being equal to the addition of A plus B, all right? And let's say that we just do a pure C, all right? Now you may be wondering, what is pure C standpoint? So I'm going to go through this uh, all the way through line by line, okay? Because I didn't want to. I haven't introduced the specific the specific uh, type class that this is referring to. Okay, so this is do is mainly used when you're dealing with monads in a lot of cases. A lot of the examples I've seen is do is often almost always used with monads. Okay, and it's putting monadic transformations together in sequence. Okay, when you're dealing with monads, the first thing you need to recognize is the fact that we need to be able to unwrap from a monad and actually get the value from the given monad. Okay, so in this example here, we are unwrapping each particular value from AX, and we are assigning it to A, as well as we are unwrapping each value from BX, and it could be one or more, and we're assigning it to B. That's what this left arrow syntax represents, okay? The let syntax here is going to essentially scope C and assign it the value of the addition, in this case, the summation between A and B. Finally, and this is very important to folks coming in and looking at this pure and wondering what the hell it is. Um, Unfortunately, the monad type class in Colton, and I think this is, I don't know if this was deliberate or because of some limitations in using return and probably it conflicting with Common Lisp. But essentially, the monad type class does not have return, which is normally associated with you lifting a value into the monadic world, okay, and then returning it, okay. Instead, what it does is it uses from the applicative type class, which again, monads are applicatives. You know, don't worry about the specifics as to why this is the case. We'll get into that when we talk about all these particular type class implementations for functors, applicatives, monads. But we're going to use the pure function from the applicative namespace to go and essentially return. Okay, so you could think of this as returning C, which is lifting it up and putting it back into the monadic space. All right, very important. Um, but I thought it would be useful to first show you the syntax before we move forward. So we've now compiled this, and now this is all good. And when we try running this, we need to pass in a monad here. Well, the best monad actually that we could probably use is list because lists actually can be defined as a monad. So we're going to go ahead and um, here define a, a list function x's that we could then just call f make list 1, 2, 3, 4, and then make list 1, 2, 3, 4. It actually, yeah, 1, 2, 3, 4. This should actually do what I expected to. All right. So, we run this. What is it complaining about? Unable to unify list of integer and integer in definition of x's. Oh, I'm using the wrong name. F prime. There we go. Value class num is not of type library class monad. Okay, let's see why that is the case. Let me do this. Do something here. And let's see here, not of type class mode. I'm simplifying the data just so that this way I can actually go and leverage what's going on here. It's a numeric type. It's not of type monad. It's a type error, but the type error it's an instance of a monad. It's not the monad itself. So I'm wondering what this type error is coming from. This is interesting. Let us see if this is saying that I'm going to be giving me okay. This might be related to the fact that the value being extracted by A is okay. I think it's complaining about pure returning this value C and trying to lift that up, which is surprising. But let me try something here just to confirm this is the case. Let's see here. We take a listen here. Hold on a second. Let me just do this. Control C, O. Do this just to compile this one more time and see what it says. Does not actually say, and it's because I'm almost certain that it's probably this one that it's complaining about. Let me just do this and just say list of and see what it does. Oh, sorry. I can't use list. I have to do make list. Make list plus AB. Okay. Still not complaining. It's still complaining about the class numeric of the instance. Interesting. I'm wondering if there's a bug here. Okay, let me do this. I'm going to, I haven't seen this here. Lovely. Okay, keep that there. Let me first look for this function f of, there it is. Let me take this guy out. Oh, crap. Open. All right, and compile that. There we go. Just do this. Okay. This shouldn't matter, but I'm just trying to clean up some stuff so that it matches kind of what the README has. Okay, so let's see here now. We have our assignment. And let's do this. And let's do that. It's still complaining, so let's do this. See what happens. What is type of F? Type of F is taking a numeric B and a monad A. That is wrong. That should not be. That should be a monad A and a monad B. That's the problem. So when you see these kinds of type errors, you can actually just spit out type of. You also actually, surprisingly, I found out in here that we also have kind of to actually determine if a is an implementation of to see if we have a higher kind of type, if we have kinds of types, which for folks who aren't familiar with, um, interesting. This should be available. I'm surprised that kind it did not work. Maybe I have to do kind of my EQ here. Unknown binding in Colton. Okay, so oh, I'm being stupid. I have to do this. Colton my EQ. What? That's weird. Hold on 1 second. Try. Let's try EQ. Nothing. This is interesting. Does not look like kind of is doing what I expect it to do. Is result. Type of result is going to complain because there's no thing there. It kind of ORD. ORD is a constant type. What about EQ? EQ we can't find. What about monoid? Find that either. That's really weird. One more, and then we can get started. We can actually see it with the example with semi-group, but I'm surprised that oh, right. I think I have to actually kinds are related to not type classes. It's related to whether or not a type has been constructed or not. So for parametric types, this becomes important. Oh, so there's a question here related to Colton's do syntax and prog-n. So Colton first does have a prog-n. Colton's prog-n basically, as we probably have seen earlier, it actually, in fact, I think I do have prog-n. Prog-n example. No, I do not. Okay, let me go ahead and generate one. So let's say that we have a function. To show this, it's probably be easier just to go ahead and construct one. Let's say G of A and B, and let's go ahead and do a prog-n to show the difference. So let x underscore equal b show x, let y underscore equal show y, and for folks who are looking at this, wondering why I'm doing equals, equals is using assignment as a basic assignment inside of Colton to actually go ahead and uh, scope it within the context of the prog-n. So it is kind of a let block, but it is a immutable let block versus like what Common Lisp provides, which is set affable let. So if we do this, oh, sorry, this and that. If we go ahead and compile this, unbinding show. Oh, I'm dumb. I forgot to also specify a signature here to actually make it so that the lookup gets constructed correctly. Sorry, not. If I do this, we should get unbinding show in definition. Weird. Let me see something. Is sly apropos show? There is no show function in that's weird. Okay, so there's no show function. Show is basically what you would use to actually go in and I thought I did this. Show. Okay. So let's go here and let's see. So the main difference is I don't believe progan. I'm sorry, I couldn't get this particular example from the README to work as I intended. It looks like the symbol isn't showing up the way it's supposed to be, which means I have to go and look up where the symbol is being described, where the symbol is available for show, and then work my way through it. Huh. It says that it's available, so I'm surprised that okay. So there's one way of doing this. So the show type class looks like it is also available. I'm surprised that it's not listed here, but show is basically how you display in most Lisp systems. But the one thing that is important to realize about that is um, we don't know whether or not a particular type exists. Sorry, a type class instance exists for all types. So to do this, there's a couple of databases already built in. So we talked about the fact that Colton keeps all of his stuff in its own environment object, but we don't. We've never actually brought up how it should do this. And earlier on, I was trying to leverage Sly to do this, but it looks like there are actually debugging stuff that related to how it's supposed to be to actually determine whether or not you are dealing with what's it uh, there's particular functions in their APIs that allows you to go and inspect the actual Colton system and Colton environment separately from what the Common Lisp provides you. It's a little bit frustrating, but it's okay. I think it's because of the fact that they didn't figure out the best way to actually go and incorporate that with this inspector that most people are familiar with without actually breaking the inspector because we are looking at a completely different environment. Um, Before I show that, there is one thing that I'm going to just kind of look at is since we were talking about kind of earlier, let's look at F for a second. Not F. Let's look at kind of. No, maybe won't work. Um, Let me look at one thing here. It was um. Let's pull up. Where is it? Okay, so let's look at this. My apologies. Kind of Boolean. There we go. All right. So the reason why I'm trying to show you kind of and talk about it a little bit is because kind of is a something that's necessarily to understand when you start doing more and more static type development, particularly when dealing with parametric types. Okay. There may be situations where you are dealing with a type that isn't fully recognized yet. When you are in this space, especially when I say fully recognized, I mean that all the type parameters have not been specified. And as a result, you have a partially recognized type. It's not actually a type that's been um, completely constructed. When you're This is kind of stemming from kind of the Haskell space, so I have to go and dig into what this is doing just to kind of bring up what Colton is providing you here. But in a nutshell, kind kinded types are essentially dealing with type constructors, okay, and data constructors. All right. When you are constructing a type, you need to specify what concrete types are needed for this parametric type in order for a further concrete type to be constructed. If there is a type that requires multiple type variables, what ends up happening behind the scenes is that it will actually construct ultimately a function that actually determines whether or not all the type variables has been specified, and at the end it will return a concrete type. Okay. In the case of Boolean here, you may notice that we're getting returned a star. In kind notation, a star means the type has been fully realized. Okay, in other words, we are dealing with a concrete type. If we are dealing with something like, say, um, what we had earlier, which was kind of result, which is a type a uh, a type constructor that requires another type, well, two types because it requires what's being returned and an error type. You're going to get something like this, which is called a higher kind of type because you have essentially multiple types that are required for it to be constructed. An example of a single kind of type is list, actually, but I don't believe I could just do maybe make list will probably give me the ability to do that. No, I don't believe so. Type of make list will give me probably something. Dynamic make list. Okay, so maybe list like this. There we go. So in this case, when we're talking about list essentially is a single argument, single kinded type. It's not a higher kinded type. It requires only one type in order for a concrete version of itself to be constructed. Okay. This specific thing here, okay, if we bring up kind of list again here, just to clear up some of the errors that were showing up here compared to result. This is actually showing us one thing about lists that I think I've iterated before, but I'm just going to reiterate again. If you are in Colton and you are dealing with lists in Colton, you are dealing with exclusively homogeneous lists. That is, every member of the list is going to be of the same type. Okay, so you can have a list of integers, you can have a list of tuples, you could have a list of characters and so on. But at the end of the day, they are all the same. Every member of that list instance is going to be exactly the same. And that is a very important thing to recognize when you are dealing with uh, types inside a statically typed system, especially one that has been, um, what's it? Been mimicked or mapped after or monitored, inspired by Haskell's type system, which Colton very much is. Okay, so that's what a kind is. A kind essentially is have we created a concrete type or not? Okay, have we created a concrete type or not? When you are dealing with a concrete type, again, if you do kind of um, integer, you're dealing with a concrete type. You're dealing with something that requires a type parameter like say list, you're dealing with a kinded type data type. And if you are dealing with something like say result that requires multiple type arguments, you're dealing with a higher kinded data type. Okay, this is kind of the construction that you're going to go through. At the end of the day, though, you are almost always going to be dealing with when you're at the end of the type checker, you are almost always dealing with concrete types. But in the process of that, you may be able to specialize and further specialize them. And as long as you're able to figure out how to construct a generic representation for a family of types, and you know such a generic representation exists, creating a parametric type and actually dealing with higher kinded types is it's actually pretty regular. It's something that you would probably use daily. Um, yeah, I forgot that I had a little bit of a brain fart earlier with related to kinds, and then it suddenly hit me. We're talking about types constructors again. So I thought it was important that we cover that particular piece one more time. Finally, there is, like I said, the the package inspection system. We've looked at type of, we looked at kind of, type of, remember, is dealing with symbols that are available in your Colton image, and it will generate essentially something like this. Then we have kind of to deal with. And yeah, of course, I know I haven't actually fixed this particular F example to show you the do notation, but I wanted to finish off the rest of the library, and then, time permitting, we'll go back to actually go and correct this particular problem. Uh, in addition to the type of and kind of functions, there's also, like I said, a bunch of functions dealing with printing stuff from the environment directly. So one example of this is print type DB. All right, print type DB prints every known type available in Colton. All right, and their signature. So in this case, you can see from Colton itself, we have all of our basic types in addition to Lisp objects. It gives you their kind. So in this case, arrow syntax is a higher kinded type. It doesn't know exactly where the types. Once the types are all specified, it'll give you kind of the arrows, the function signature. List is a sorry. List is a type that's dealing with essentially one argument, one type argument, and then is returning a concrete type. You have support for characters, unsigned integers, both from 64-bit down to 8-bit, all for both unsigned and unsigned integers. And additionally, we have a bunch of kickbutt types in the Colton library. So this is core Colton, if you want to call it that. And then the Colton library provides things like, say, graphs, nodes, edges, cells. It'll provide you essentially the ORD. I'm guessing that's orderable, but that's surprising. I thought that was a type class. Um, Fraction, it has optionals, so we have the ability to create optionals now. Tuples up to 5 elements. Result types, which allows us to also specify errors, kind of things. Slices, which is dealing with how to get essentially views from a collection. Hash tables, as well as a couple of ones that I don't know in what cases they would be used. So if the Colton authors can join us and kind of specify or kind of tell me a couple of the other ones like target node and quantization and when those are particularly used, I would be more than interested, and I think our audience would be more than interested to deal with this and look at what these are providing. In addition to that, we have also something called print value DB, which gives us everything that's specified in the current Lisp image in the current Colton environment. Okay, so you can see this can be used to actually look at all the functions that are actually given to you at your leisure. You can actually look at everything that's provided there. And for each thing that's provided, it gives you the full type signature. So this gives you a lot of information for you to actually go through and look up specific stuff. Then print class DB is used to actually specify all the type classes available to you. All right, you have in our case from the Colton Library, unwrappable, quantizable. We've talked about that the couple things that are available for you know semi groups, monads, monoids, functors, and so forth. And these are all the other ones that are also available. And it gives you what operations are required in order for things to be of that particular type. So this is something that's important to be aware of. The one thing to note, again, like I said about monads that you need to really consider is the fact that we have this pure function instead of return. Again, I don't recall reading anything in my digging into this library to determine whether or not, um, you know, the reasons why they chose pure versus return in the Haskell syntax. And then, finally, we have print instance DB, which honestly is going to be very, very useful if you specify the package. So let's say Colton Library. And this is going to, oops, package symbol, I guess. Yeah. CL find package designator, Colton Library. I think I can do that. Yeah, there we go. This is a very important thing, and I wish there was some more integration with this, but this is essentially what I was trying to show earlier. This is essentially for every type class that's defined in your image. I just restricted it into the Colton package. It's going to go into every package, find all the type classes, and find all the instances associated with all the type classes. This is particularly useful to know what's been defined and for what. So, for example, this is all the instances of the numeric type class defined. And as you can see, it is defined in all of the major Colton types that are specified in the core Colton library that we saw when we printed print type DB. And it also, which interesting enough, I didn't realize that they have a cell. It has uh, defined type class instances for the floating point integers. So this essentially is a fairly complete implementation for numeric types. I encourage you to go through what's available here. I hope at some point um, uh, there is a way to actually integrate this into the dev environment so that it's a little easier to actually go through and explore. Obviously, I'm not making requests here. I understand that it's craziness. If I have at some point, I would probably try to do some of the experimentation myself. But the fact that we can actually create type classes, define instances of type classes, and get all that information introspected in a seamless fashion using an API to me is beautiful. It allows us to essentially develop in the same way that you would develop in Haskell without ever actually leaving your Lisp image, which I'm not going to say that I have a soft spot for Common Lisp, but I'm just like asking now, like if we could do this all in Common Lisp. Um, anyway, I don't want to start a flame war or anything like this, but this is just really impressive. All right. Um, it's just I'm excited that this has its uses and stuff. So I'm gonna pause here again for questions. And in the meantime, while I'm waiting, I'm going to go ahead and start looking into this other thing related to the pure syntax. So this one looks like it is. Let me do this. I don't know if I could do this, but I probably could go and restrict this by just saying declare f as being monad a monad b equals um um I really didn't want to specify this way, but we'll see what craziness it's going to entail. A, B, and then monad C. And let's see what happens here. Oh, there's something about unknown type monad. What? Okay. It is not a monad. Maybe I don't have to specify. Oh, should be specifying the here. Okay. Do that. Unveiled unified types of monad T332 and T1798. So I'm guessing these are symbols that are being generated during macro expansion. Yeah, this is all related to macro expansion. So, okay, folks, I'm going to go ahead and do this, and going to go ahead and looks like though show is here somewhere. It's let's do this. Print class db cl find package Colton Library, and let's see here. Order num is I go ck. Okay, so it doesn't look like they've defined a show here, which is a little disappointing, but we can always go and fix that. That's because show is actually pretty easy to implement in Common Lisp. The show type class is nothing more than uh, from string or something like this, and then you can actually go and just do a redirect into the printing API that's available in Common Lisp. But I guess that's not what they want. Okay, so I will go and fix that other one later. Let's do. Let's see. The type of f should now say num a monad. What? What is going on? Let's see here. Where's the do syntax? Maybe I messed up the. Okay, hold on. I rewrite all this. Do a arrow ax. Let me just start with that. See what happens here. Obviously, it's going to do block cannot just be a binding. Of course not. I just wanted to see if it's going to work. B A B X, and let's see, pure list A, make a list AB. Okay, there we go. Let's see what happens here. If I do type of F now, it should say boom. I think I got it. Think. No, it just says monad A, monad B. Okay, let's see what happens when I do F. Make list 1, 2, 3. Make list 4, 5, 6. Let's see what craziness is there. Invalid arguments 2. All right. There is some craziness here that I'm not understanding. It is let me do this. Colton U. I shouldn't have to do this, but let's see what happens. Oh, sorry. Library U. There we go. Still actually taking. Oh, I'm dumb. Let's see. Let's see, what did I just do? If I do make list 1, 2, 3, what is it gonna do? Invalid arguments 1. Why is it invalid if I just have? This is interesting. This requires. So first off, this should not be a problem. Then let's do let c equals plus a b. Okay. And let's see why this c. I do type of a, what it is. Let me not even specify C. Let me just do C like this. See what it doesn't complain. It did not complain. That's interesting. We're now just playing around here. I'm just trying to see what's going on with this issue. A is some sort of monad. Oh, okay. Got it. So the first type parameter is going to be the monad that we're going to try and create. The second one is then going to be leveraged. Okay. So let's see this. I don't know if this will work, but this list didn't think I need to do this, but we'll see. Integer. I'm sorry. I have to specify list like this. List is not of type class monad. Okay. That's weird. So what is of type monad? Which we could find out now because print instance db will tell us exactly what we are looking for. Find package Colton Library. And let's see what is of class monad now. Monoid monad. Sorry, wrong one. There it is. It says list is a monad. So there is an implementation of list being a monad, which is why I'm surprised it's complaining. Oh, right. List alone isn't a monad. It has to be a list of integers because it's a higher kind of type. Okay. Shoot. Oh, this is the kinds of things that you get into when you're dealing with monoids and monads and all sorts of crazy stuff. All right, so now I have to first figure out how to subtype symbol. Fine. Hold on. Define a list. Make a list. 1, 2, 3, 4. Okay. Okay. Hold on. Colton. Sometimes some of these things work in the Colton in the regular REPL, and some they do not. So I have to go back into this. Define a list. Make list. 1, 2, 3, 4. Okay. So now I can do type of a list, and we see that it's a list integer. Let's do this. Okay. We are going to do, guessing I'm going to have to do this. List integer. Okay. And guessing it needs to specify the return type too, which is integer. And make list 1, 2, 3. Make list 4, 5, 6. And what happened? Is not of type monad when binding. Okay, so let me see if I could just specifically say that is monad list. Interesting. Really, you shouldn't have to do that. You should be able to just do this, and it should recognize that from the type. Let me see if I do this. Colton F make list 1, 2, 3. Make list 4, 5, 6. And see what happens. Unable to unify types integer and list of integer. Okay. Let's do one more experiment here, which is lifting pure C here. And then try this. Oops, sorry. One, this. So I'm going to have to debug this a little bit more in detail just because this is interesting. What it's doing is it's determining that because we're using do notation, A, the first type of A that you're dealing with must be some sort of monadic type that's going to be passed into the function. The second argument that it's providing here is saying that it's going to be some sort of numeric type because we're using we're extracting from the actual monad the values from that type and we're adding them together. Okay, the fact that we're using addition is the reason why it recognized that the second type variable has to be an integer. And what it's now saying is in the signature, if you look at the signature is basically saying we're taking a monad of type B and another monad of type B, and we're returning a monad of type B. Now, unfortunately, for some reason, once we've actually extracted these things, it looks like it is not recognizing the fact that at least has defined by the README. And, I've had trouble with this in the past where they made a change and it doesn't actually work in my current version. But if I pull, maybe I should do that one quick second here. If I pull the latest version of Colton, because the Colton is not available in Lisp, you have to actually go and clone it. If I pull it, maybe it might have some new stuff. Let's see. Okay, let's go ahead and restart our Lisp and see what happens. Let's go ahead and do this. Sly, restart inferior Lisp. Okay, and now we go ahead and reload our quick load AFP Colton overview, and this should actually work normally and you'll be okay. The reason why it's taking a little bit longer is because we're recompiling behind the scenes. Set the package being AFP Colton overview, and hopefully if I do make list 3, make list 4, 5, 6, and I do Colton CL CL print Colton this wait, this it's still determining that it's although it's a monad of type integer, it is not determining. For some reason, I think in the plus operator, it's not actually constructing what we're expecting here. So I'm wondering if I could just do make a list here one more time. Let's see what type of it is this time. This should still match. Okay, I'm forcing it to be a list here. So if I do F, make list 4, make list 1, 2, 3, 4, should work. Invalid arguments. Let me do this. Make list 4 and see what happens. Invalid arguments 1. So what is F then? So it looks like I'm going a little over right now, but so I'm gonna hold this off till next week because it'll give me some time to actually go and debug this. Next week we're gonna actually start diving into a couple of these type classes that are available. Um, Specifically, we're gonna work our way through defining a monoid, a semi-group to a monoid, and work our way up to essentially defining a monad. Um, Point question define name. No. So there's a question regarding the definition. Define it takes if you're defining a function, which is what I'm doing here. The syntax for the definition is actually um, the scheme syntax where you specify in the first argument of the S expression the function name, then you specify the arguments. So if you look an example, and we've actually created a couple of examples of this before. Here we are defining a function that takes in a numeric value x, and we're returning a numeric value. So if we look at the type of this, you'll see that it's an integer and then returns an integer. Other questions from other people who are watching? Okay, well, I'm gonna debug this a little bit more. Hopefully I can figure out what's going on there. And until next time, folks who are watching this series on Colton, if you guys have any questions, please, please, please put your questions into the YouTube comments so that way we can address them in the next episode. Additionally, those of you who are on Twitter, feel free to tweet us and tweet about the Common Lisp study group. I'd like to, uh, and we'd appreciate the promotions. Finally, to the Colton authors who are paying attention closely to this tutorial series, if I have made any mistake, by all means, please contact me. I'm Bugram on the Functional Programming Slack channel, as well as I tend to squat in the Lisp Discord server. If there's anything that needs to be corrected, I am more than happy to go in and create another episode to correct them. My intention for this series is to actually provide more of a detailed overview than what is provided in Colton, rightfully so, because people need to actually understand how the library works. And I'm hoping that hopefully by promoting this good library, folks will actually go in and um, take a look at this. And I hope our viewers who are watching, you guys are excited as I am for actually leveraging this library, although there might be a couple of kinks on it because it is still, being working towards a full 1.0 release. So while you're working through your projects and stuff like that, by all means, send your GitHub issue requests and post them up so that folks can realize that, hey, this is actually coming together. And hopefully we'll see a really good, mature implementation in months to come. But you know, I'm not going to take too much time on that. I hope all of you have a good holiday. We are going to be still having our stream next week for the Common Lisp study group as well as folks who are watching. We will be airing our Haskell study group tomorrow from 7:40 to 9:40 p.m. Eastern Time, and we are still going to have that also next week too as well. So until next time, I bid you all farewell. Have a good holiday, and see you next week. See ya.